In this video, we're going to look at some integral evaluating strategies. We're going to do 3 examples, and each of those examples is going to include some trig. So our first example here, we have the integral of cosine x times sine of 2x plus sine of x times cosine of 2x, integrating with respect to the x variable. Now, one thing we need to make sure we remember when we look at problems with trig in them is we want to consider our identities. And one such identity should jump out at us. This is a sine sum identity. And one way that we write this is we might say that sine of alpha plus or minus beta, you should recall this from your trig class, equals sine alpha cosine beta plus or minus cosine alpha sine beta. So this, looking at what we have here, all of this, we could consider x to be my alpha and 2x to be my beta. I can rewrite that now as the sine of my alpha plus my beta, which would be x plus 2x. Or rather, we're now integrating the sine of 3x. And this can be done with a u substitution or just knowing the formula. I'll work out with the u substitution here. We have u equals 3x, so then du equals 3 dx, or 1/3 du equals dx. This becomes the integral of sine u, and that dx becomes 1/3 du. The integral of sine u is negative cosine u, so I have negative 1/3 cosine u plus c, and subbing back in my x value, we always have to do that when it's an indefinite integral. If we've got bounds, we can change everything into u and we don't have to worry about going back. But because this is indefinite, as opposed to a definite integral with bounds, we have to put our x's back in there. So we've got negative 1/3 cosine of 3x plus c. And so just recognizing that there was an identity hidden inside our integrand, then it was much easier for us to integrate. Looking at the first step, we didn't know what to do. So when we're dealing with trig, one thing we want to remember is to look for some of our identities. And the important identities that I would expect you to know would definitely be your Pythagorean identities, your sum and difference identities, as well as double angle identities. I personally don't think the half angle identities are as important, but we do use them a bit in Calc2, so you should be familiar with them. And remember, any half angle identity can be derived if you know the double angle identity. All right, let's move on to another example. For this example, we're going to evaluate the integral. This is a definite integral because it has bounds. The last one was indefinite. We're going to evaluate the integral of 1 over 1 minus sine x, and we can pull that dx over here at the end. All right, so when we're dealing with integrals that look like this, one strategy that we often use is to multiply by 1. And we multiply by 1 by considering the conjugate. So in this situation, what we have, we've got the integral from pi over 4 to 0. As I said, that is 1 over the quantity 1 minus sine x. And my dx is over here at the end. But I'm going to use this concept of multiplying by 1. I'm going to say, well, this is 1 plus sine x over 1 plus sine x. And so my dx is still there. So this quantity I've written in yellow, this is equal to 1, and I picked it by looking at the conjugate. So this is something we do a lot, and especially when we have radicals as well. So looking at this, if I think about simplifying that, I've got 0 to pi over 4. I've got 1 plus sine x is in the numerator, and my denominator, when I multiply that, that's a difference of squares. I've got 1 minus sine squared x. So at this point, we want to recognize that we see an identity in here. So as I mentioned, we know our Pythagorean identities, sine squared x plus cosine squared x equals 1. And if I rearrange that, I can see that cosine squared x equals 1 minus sine squared x. So this, my denominator here, 1 minus sine squared x, that is equal to cosine squared x. And I'm going to do that substitution. And so when we see anything that looks like this, we multiply by that conjugate, we know we're going to be able to use that Pythagorean identity. The reason we wanted to do this is we want that denominator to have only one term. So what we have, we've got 0 to pi over 4, 1 plus sine x, and I have cosine squared x in the denominator. So the reason this is nice is now I have only one term in the denominator. That's going to allow me to split this integral into the sum of two rational terms, two fractions. So here I now have the integral from 0 to pi over 4 of 1 over cosine squared x dx plus the integral from 0 to pi over 4 of sine x over cosine squared x dx. Now, 1 over cosine squared x, that is reciprocal identity. We know that is secant squared x dx, and I like that because I know the integral of secant. And similarly, with sine x over cosine squared x, that's the same as sine over cosine times 1 over cosine. Right? So looking at this, this is the same as sine x over cosine x times 1 over cosine x. So sine over cosine is tangent x, and 1 over cosine is secant x. Looking at both of these are both values that we, or integrals that we know from our table. Using the table that corresponds to our book specifically, we're looking at integral 8 and integral 10. So the integral of secant squared is tangent x, and the integral of tangent times secant is secant x. And of course, this now needs to be evaluated between pi over 4 and 0. So I have tangent of pi over 4. I like the way that looks. Tangent of pi over 4 plus secant of pi over 4. And then I'll plug my 0 value in, minus tangent of 0 plus secant of 0. Tangent at pi over 4 is 1. Secant at pi over 4, remember at pi over 4 on my unit circle, right up here, pi over 4, my ordered pair would be root 2 over 2, root 2 over 2. So secant is going to be 1 over that cosine value, 1 over root 2 over 2. We'll simplify to just square root of 2. Tangent at 0 is 0, and secant at 0 is 1. You'll notice that 1 minus this 1 go away, and the value of my definite integral here is equal to square root of 2 exactly. All right, I would like to just incorporate one more common trig integral into this video. So I'm going to add that here next, third example. For our third and final example in this video, we're going to look at a definite integral. Negative pi over 2 to pi over 2 of the integrand is x cubed times cosine x. In this case, we have trig. I do not clearly look at this and see, okay, this is an identity. And a strategy we can oftentimes use when we're trying to figure out an integral, and I strongly recommend that you do this, is to plug it into your graphing calculator. See what the shape of this curve is. We always want to know what we're dealing with and what we're looking at. So I'm going to pull the graph in. Looking at this graph here, from negative pi over 2 to pi over 2, we are considering these two shaded regions, okay, that I've just shaded in here. And what you'll notice is it looks pretty symmetric, right? So this is a symmetric integral. One thing we know is that above the axis is going to give us a positive value, and below the axis is going to give us a negative. So if these are the exact same positive and negative valued shapes, they're going to cancel each other out, and we know our integral value is going to be 0 since this is symmetric. It's an odd symmetric function, and odd functions have rotational symmetry about the origin. So we can describe this and we can say this is an odd function, and we're considering it across a symmetric interval. All right, so we have an odd function across a symmetric interval. And you may need to prove that a function is odd. Well, remember what our definition of even and odd functions is. F of negative x, if I plug negative x in and it returns the opposite function, negative f of x, then that would be representative of something which is odd. And f of negative x returning the exact same function, the negatives cancel, then that would be even. Oh, that's a weird N. Even. So one thing that we know, x cubed, we can prove that's an odd function, right? So x cubed is odd, and we know that cosine x is odd. Those are very easy for us to show. And the product of two odds would also be odd. And we can verify this algebraically as well. F of negative x. So remember, my original function, f of x, is x cubed times cosine x. So what does this look like if I plug in negative x? So negative x cubed is negative x cubed. A negative times a negative is positive, times a third negative would turn that back negative again. And we know we have an identity, cosine of negative x is equal to cosine x. So factoring a negative out of this, this is negative x cubed cosine x, or rather negative f of x. Therefore, it is an odd function. We are considering this odd function across a symmetric interval. We know that that top and bottom are going to be canceling out. We're going to get a 0-valued definite integral here. So in this video, I looked over 3 different trig examples. Please, as always, email me if you have any questions.